Okay. So this is a talk about some work. Oops. Oh, it's in. Okay. This is a talk about some work with Varun Grover, my colleague at UCSD, and my former student Daniel Ben-Zion. And Mike did actually give a good framing of what I'm going to say, but to maybe help a little more, let me tell you a story. So in biology, they have this sort of creation myth by which they distinguish between some of their subfields, in particular between biochemistry and genetics, which goes as follows. Actually, this was written by, as you'll be able to tell, by a geneticist named Bill Sullivan. And so the story is that there's a retired biochemist, Doug, and a retired geneticist, Bill, who live on a hill overlooking some automobile factory, and having spent their whole lives doing science, they don't know how cars work, and so they decide to use the tools of their respective disciplines to figure out how they work. And so the biochemist buys 100 cars and grinds them up and discovers that cars are made of 10% glass, 25% plastic, and so on. And the geneticist who wrote the article instead drinks some tea, and then he goes and ties the hands of one of the workers at the factory, and then goes home and drinks some more tea, and then watches as the cars that come out of the factory that day are missing the steering wheel, and they fail to make the turn, and they pile up on the grass, and so in this way he discovers that the steering wheel steers the car. And so, it goes on with lots more gloating by the geneticist. Okay, so I want to make an analogy that the thing we've been doing all this time is like the biochemistry approach to understanding entanglement of quantum many body states, where we start with some state and then we grind up part of it by taking the trace over the complement of some region. That's the analog of the grinding. And then, in this way, we take various combinations and say that, there's this fraction of topological entanglement entropy and this fraction of both. Okay, so what I'd like to propose as the analog of genetics here is instead to proceed using the observation that by measurements we can destroy entanglement. So actually, the way in which the word disentangling in my title is a much less subtle process than it will be in Lucas's. I'm sure we're just going to destroy the entanglement by making some kind of measurement, and then use the properties of the measurement, the wave function that results after the measurement to learn something. So in this way, we can make a simpler wave function which we can understand. And in the examples that I'm going to talk about, I'm going to focus on systems where each point in each site of the system has multiple components. So we can easily make some decomposition of the local Hilbert space into two parts, like, for example, in a Hubbard model into some spin degree of freedom and a charge degree of freedom, or in a Condo lattice model between some conduction electrons and some local moments. So built in the examples I'll talk about will be this sort of natural decomposition, and we can measure part of them and see what happens to the rest of them. So here's the sort of protocol that we're going to follow. So the idea is, decompose the system both by this local label that I described and into some regions of space. So the Hilbert space decomposes into some tensor product of parts. We can do a little bit of tracing if we want. So trace out what's called D. Maybe D is empty. And then, in addition, choose some operator that acts on the subsystem C. And so starting with a state of the whole system and a choice of operator here, we measure this operator C, operator X on C, and obtain some outcome with probability according to the rules of quantum mechanics. And I'm going to assume, this will be an important assumption here, that the outcome of that measurement on C provides a basis for C. So that making this measurement completely specifies the state of C. So measure all of the positions of the particles in that region. And then in that resulting state, which has this form, we make some whatever measurements you would have made otherwise. So for example, we could find the entanglement entropy of some further subregion, some subsystem A. And then, so this depends on the outcome of the measurement. And so the simplest thing to do then is to take some average over these results, weighted by the probability of having obtained that outcome of the measurement. Okay, so I'll call this the QDL diagnostic. And to explain this acronym QDL, it stands for quantum disentangled liquid. Oh, sorry, before they do that, sometimes, instead of measuring the entanglement entropy, it might be interesting instead to measure the mutual information between two of these subsystems, some measure the correlations between the remaining parts of the system. So I'll call that IQDL instead, if we average instead the mutual informations. to explain why I call this the QDL protocol, it's because this sort of protocol was introduced by Grover and Fisher as a way to diagnose a certain failure of ergodicity that they were conceiving, which it's sort of in between many body localization and an ergodic state. And the situation that they had in mind is where we have a system made of two kinds of particles, one class of which are heavy and one class of which are light. And they envision a state where the heavy particles are in some perfectly ergodic state. They move around and have a volume law entanglement between themselves. But because the heavy particles are heavy, the light particles see them as sort of a frozen background. They create some random potential. Each configuration of the heavy particles instantaneously creates some random potential for the light particles, which can localize them. So MBL is the limit where the masses of the heavy particles becomes infinite. And so the wave function has some form like this, where for each configuration of the heavy particles, the heavy particles have some ergodic wave function, like some Fermi liquid kind of wave function, something like that. And and for each configuration of the heavy particles, capital R, there's some fixed wave function of the light particles, which is like a MBL wave function, is a localized wave function. And so although the whole state, if you measure the entanglement entropy of some subregion, would give a volume law from the bath of heavy particles, if first you measure the positions of the heavy particles, so then the wave function up to some normalization is just this part, that's an area law wave function. And so if we do this QDL protocol that I just described, we find, on average, we'll find an area law for that quantity, which is sharply distinguishes it from other phases. And this phenomenon actually happens. It happens in the Hubbard model. So in a 1D Hubbard model, and before you say that it's a consequence of integrability, they add a integrability breaking term, some near neighbor interaction which breaks integrability, and so this is a picture of the full spectrum of some 12-site realization of this. This is the energy, and this is the double-on fraction. So this is some local operator, and so the very fact that you can distinguish these red guys here from these blue guys here at some fixed energy means that it is a violation of the eigenstate thermalization hypothesis. It's two states with the same energy where a local operator has a very different behavior, and you can also they call these spin band states. And you can also see them in the behavior of the entanglement entropy of the small subregion as a function of energy. So there's this sort of totally other system living inside the Hubbard model, which are these spin band states. And so this is a picture of if they do this QDL protocol in one of these ergodic states up here, the answer is a volume law. And if they do it in one of these special states, like these green ones, the answer is an area law. So this actually happens. Whether it happens in the thermodynamic limit isn't clear from this calculation with 12 sites, but I would say the evidence for the existence of this phase is about as good as the evidence for MBL from numerics. Okay, so it's something that happens, and so the idea of this project is to apply the same sort of strategy instead of to these questions about quantum thermalizations, to apply it to questions about ground states and topological phases and things. And then we'll come back to the failure of ergodicity at the end. Okay, so here's an example of an application of this strategy. It's very simple. So you all know that the spin 1 chain has a SPT phase named after Haldane. So for example, a phase diagram as a function of this parameter, this SZ squared term, if I make that big enough, eventually I'll get to some product state of SZ equals 0. But at small enough values of this parameter, there's a SPT phase which we could diagnose by edge states, or perhaps more generally, some doubly degenerate entanglement spectrum. That's a sort of sharp signature of this phase, which is robust to breaking lots of the symmetries. And okay, so this one we understand. We understand the wave function of this, but here's a thing to make it harder. So suppose we dope this model. So that is, think about these spins as arising from spin 1 bosons, which are able to hop. And suppose I dope in some holes into the system. So here's a picture of each of these things is one of these triplets. And suppose there are holes that can hop around. But then when the spins are there, they interact by the same kind of Hamiltonian. And it was some evidence for the following phenomenon was given by these folks that the phenomenon of spin charge separation happens. That is, we can think separately about what the charges are doing, what the spins are doing, and the charges form a Luttinger liquid, like you might expect them to in one dimension, but the spins basically leaving out the sites with the holes form a Haldane phase. And so the phase diagram looks something like this. There's a phase which is an ordinary Luttinger liquid, which corresponds to this trivial phase, and then there's a phase where the spins do this interesting SPT thing, but in the presence of this gapless bulk. So gapless SPTs are a big subject, of which this is one example. I'm going to give an overview talk about them tomorrow, which include, but for now, the question we want to ask is, how would you tell if you realize this phase? And so one way to do it is simply to freeze the charge degrees of freedom by measuring the positions of all the holes. And so according to the kind of diagram I was drawing earlier, we make some decomposition of the Hilbert space where C, the subspace that we're measuring, is the charge degrees of freedom, and then we decompose the spins into A and B. And if in this topological Luttinger liquid phase, we measure if in this topological Luttinger liquid phase, we look at the entanglement spectrum, for the full wave function, it looks like this messy thing. But if we first measure the positions of the holes, then we get some random configuration of the holes. But for whichever one we get, so here's 3 examples, we get this doubly degenerate entanglement spectrum, which is a signature of the Haldane phase, which is left over. And I guess it's also useful this diagnostic is also useful for thinking about the phase transition between this topological Luttinger liquid phase and the trivial phase. So here I'm plotting. So this is the QDL diagnostic, the lower curve in each case, and this is just the entanglement entropy of a subregion of the full wave function. And so in the SPT phase, this behaves like a C equals 1 CFT, as you might expect from a Luttinger liquid. It's exactly the same in the trivial phase. It's still a Luttinger liquid. And at the phase transition, it has C equals 2, as you might expect, because the spins are also becoming gapless. But the behavior of the QDL diagnostic is just totally area law in this phase and totally area law in this phase, and in between you can see this C equals 1 CFT from the spins. So okay, I mean it's a simple example, but I think it's at least illustrative of the utility of this perspective. Another kind of system in which this sort of logic is useful is in thinking about Condo lattice models and thinking about heavy fermions. I guess nobody's talked about anything like this so far. So let me just briefly describe the situation. We have some conduction electrons hopping around. Imagine that this E of K describes some Fermi surface, the Fermi surface band structure. And then they're coupled to local moments, so spins at each site, capital S, by this Condo interaction where little s is the spins of these conduction electrons. And then the local moments can also have their own interactions. And this model hosts some rich collection of phases which we can organize according to 2 axes, one of which is the extent to which the local moments order, and the other of which is the extent to which the Condo effect happens. So this, okay. And this is a mean field phase diagram which shows that at least some of these phases can actually be realized, at least in mean field theory. But I said this axis is to what extent the Condo effect happens. It's actually surprisingly difficult to quantify that. One way to quantify it is to introduce a parton construction for these spins, like Chang-Wang described, where we decompose the spin into some fermions. And what I mean by the Condo effect happening is that there's some hybridization between the conduction electron and this slave fermion. But this as in Chang's talk, introducing these partons comes with a gauge theory. And this operator that I've written here is not a gauge invariant operator. It's charged under that gauge theory. And so that, we should really think of this as some kind of Higgs field. And so the phases where this B object is ordered are Higgs phases. And it'll be useful and interesting to have some way to distinguish them in terms of some actually well-defined observable, rather than this gauge non-invariant object. And I guess I'm using the word observable in a very Platonic sense. Okay, and so this Higgs phase is interesting. One reason it's interesting is that it has when this B is non-zero, the local moments participate in the Fermi surface. So we have a large Fermi surface. So here's the strategy. So suppose, following the logic I've been advocating, we were to measure the positions of all of the conduction electrons in this heavy Fermi liquid phase, where the singlets are participating in the Fermi surface. We'd be left with a state that knows about the Fermi surface, a state with where we can expect there to be some log violation of the area law. That's a general signature of a state with a Fermi surface. And if we didn't measure the positions of the conduction electrons first and computed the entanglement entropy of just a subregion, we would, in addition to that expected log violation of the area law, we would get some volume law term coming from the local entanglement between the conduction electrons and the local moments. And to make it a little more precise, let's think about a geometry which is a torus, where we cut the torus into two cylinders, and the size of this cylinder is LA, and LY is the circumference there. So one way to extract this information about whether or not the conduction electrons are participating in the Fermi surface is to take some combination of these things where the volume law term cancels out. And so one such thing is this mutual information. And I'm writing it as a condition. Yes, please.
Why is it a volume law? Are you talking about a ground state?
Yeah, ground state. So the thing I'm describing here is the entropy of just the local moments. So the subspace of the Hilbert space, which is where I make a cut in between the conduction electrons and the local moments. And because there's conduction electrons and local moments at every site, that produces the volume law.
It's not a cut in space, it's a cut.
That's right. It's a cut, well, in both space and in the species label, exactly. So that's what produces this volume law. And so we can get rid of this volume law by taking this combination of entanglement entropies, which I want you to think about it as a conditional mutual information, where we're conditioning on the state of the system that we're measuring. So if we didn't measure all of the conduction electrons, this would make a difference. But because of the fact that ABC here is pure, it actually doesn't matter. I could have just have called it the mutual information. So if we measure this so first of all, if you do it at half filling where there's no Fermi surface, we don't see anything at all. If we measure it in the small Fermi surface phase where there's no Condo effect, we see in the conduction electrons there's this is the mutual information as a function of log L sub y. We see that there's this violation of the area law. The fact that this thing is linear in the log says that there's this signature of the Fermi surface. And but the behavior of the local moments is trivial. And then if we measure it in the phase where we expect the local moments to participate in the Fermi surface, they both have this log violation of the area law. So this is a sharp distinction between the heavy Fermi liquid phase and the phases where there's no Condo effect. In this case, we didn't actually do the QTL protocol. It was only the spirit of it which inspired us to consider this combination of things.
Is the middle plot really different from the right plots? Like it just has a small slope, or is there something more different than that the slope is small instead of large?
Do you see a slope? I don't know.
I thought I was looking at the blue line.
Yeah, no, the blue line is the analog of this blue.
Oh,
this
I
is the
see.
conduction electrons, and this is the. Yeah, it's pretty good, I think. So actually, in the interest of full disclosure, if we do the QDL protocol rather than this thing inspired by it, it's a little more ambiguous. Yeah. Okay. So this thing I've described is actually to be honest, I was doing some biochemistry here, according to my analogy. And so you might ask, is there some relation between the result of this QDL protocol and sort of more ordinary information theoretic measures that we usually think about? And actually, it's possible there are many such relations, and we actually proved some of them. So there are some relations in particular with information theoretic quantities, which you might call conditional information theoretic, conditional measures, conditioning on the behavior of the thing that you measure. So for example, the conditional entropy is the entropy of A with C minus the entropy of C. That's the definition. And here's a proof that quantity in any state is bounds below the QDL quantity. And I guess the only thing we used here is the monotonicity of the relative entropy under a quantum channel, which basically means anything you can do to a density matrix that keeps it a density matrix. And the particular thing that we have to do to it is measure the observable XC that I described, but don't look at the answer. So if you do that, then the resulting density matrix is this distribution on the outcome tensored with the resulting density matrix of the subsystem. And so here's a picture of what happens in some Haar random states. This is the QDL quantity. This is the conditional entropy. And so this is just a lower bound. And I guess it'd be interesting to be able to do better because this conditional entropy is notoriously can be negative quantum mechanically when the subsystems A and C are highly entangled with each other. And so something else that may be useful is we can bound this mutual information QDL quantity on both sides by this conditional entropy, so this conditional mutual information, the same quantity that appears in the topological entanglement entropy. So the same IABC appears on both sides here, but the difference between the lower bound and the upper bound is this quantity here, which I learned recently is called the quantum discord. It's a thing which people have introduced to try to quantify how quantum is the state rho AC in this case. So these are some plots to illustrate that if we look at some Haar random states on small systems, this mutual information, this is the mutual information QDL quantity on this axis, and this is the conditional mutual information. So this is this axis is this guy, and this axis is the thing that appears both here and here. The pointer can't point at two things at once, yeah. And so you can see that. So here the thing I'm varying is the sizes of the subsystems in which I'm considering a Haar random state. So you can see that there's certainly no bound that says that one is bigger than the other. But if I average over a whole bunch of these Haar random states, they both exhibit the same volume law scaling. So they know about each other, I guess is the way to say it. And so actually this parable that I was telling you about earlier has a sequel which the biochemist wrote as a sort of revenge, where the story is very similar except that the biochemist wins. And so actually given what I've said on the previous slide, certainly sometimes it's easier to compute these sort of more traditional mutual information theoretic measures. And so let's see whether they can distinguish between a QDL state and an ergodic state. This is like the revenge of the biochemists. So consider in an ergodic state what would be the behavior of the conditional entropy, where A and C are two subsystems of the ergodic state, and let's treat it as if it were just a Haar random state. So in that case, the entropy of a subsystem just behaves like this, like Page's rule, and so if we plug that into the conditional entropy, we find that it should be a volume law. In contrast, if we use a model wave function for a QDL state that Thrun and Matthew introduced, we can estimate what should be the behavior of the conditional entropy in this state. And for example, in the case when A and C are the same size, it has this very funny behavior. It's a volume law, but it's a volume law with a minus sign and with a coefficient that decreases exponentially with system size. So this is a very different behavior, which offers also a sharp distinction between these two things. And if we evaluate this in the Hubbard model, the same one that those folks studied, this is the answer for the spin band state, these special states here, which exhibit QDL behavior, and then this is the volume law in a more generic ergodic state. And actually, that other conditional information measure that I described, the conditional mutual information, also gives a similarly sharp distinction between these. And this being a project with Thrun, it wouldn't be complete until he convinced me to compute the negativity, the entanglement negativity of a state. And the reason this, bless you, the reason this is worth mentioning is that a QDL state is sort of designed to have a trivial negativity. So the negativity is, I guess I should say why it's important. It's a measure of mixed state entanglement. I'm sure, oh, okay. The von Neumann entropy is a wonderful measure of entanglement in pure states, but in mixed states it also includes classical correlations, which have nothing to do with quantum mechanics. And so the negativity is a computable way to extract some measure of how much actual quantum entanglement there is between a subsystem and its complement in a mixed state, and it's defined as in terms of this partial transpose operation on the density matrix. You do a transpose just on the subsystem of interest, compute the eigenvalues of the resulting matrix, and take the log of their one norm. And in a QDL state, this reduced density matrix for AB, A and B are just the light particles, is a convex combination of these area law states, and so, which necessarily results in an area law behavior of the negativity. And how am I doing on time?
You've got 1 minute.
All right, perfect. And so some of you may know that even in thermal states of a local Hamiltonian, the negativity behaves as an area law. So that seems like it's not different. But we can actually use this to distinguish the QDL state, because even in an ergodic system, you have to trace out more than half of the degrees of freedom in order to get a density matrix that approximates a thermal state. If you trace out less than half of the things, it's not enough of a bath to thermalize your subsystem. And so the negativity of trace of less than half of the system actually also obeys a volume law. And so indeed this happens. I should have, yeah, okay, so you can see that this is the behavior in the QDL state, and this is the behavior in the more ergodic state. And, the way that we make the bath less than half is just by considering a sector where the magnetization is 2, so there are fewer spin degrees of freedom. Okay, so that's the end. I think there are a lot more things that we can do using this perspective, which maybe I won't say anything about. Maybe I have to say, in the Condo lattice model, the most interesting phase is the FL star phase, which I didn't say anything about, but should also be amenable to being diagnosed by this kind of strategy. Okay, that's the end. Thanks. Max.
Couple of questions, Max?
So coming back to the Hubbardian chain, do you understand why it works?
Do I understand why it works?
Yeah, because you're doing some, do you understand like from some field theory point of view, boundary state, but...
I don't have a deeper understanding than just the idea that the spins and the charge do what they want, so independently of each other. That's the reason that I expected it to work.
It's particularly surprising at the critical point that you get the C equal 1 for the
It's plus or minus 10% or something in the central charge, but yeah.
That's from DMRG calculations, is it?
Yeah.
Presumably you could go to my...
You could do better. Yeah, I think so. Yeah, I was surprised by how well it worked. Yeah.
All right, if there's no more question, we should probably move on to the next talk. So let's thank John again.
Do you want this?
And the next talk will be given by Lucas Witkowski from University of Washington, who will also